Okay, so here we're going to use another Taylor polynomial to approximate the exponential function by finding a polynomial representation that models the exponential function e to the x near a equals 0. So e to the x is one of the easier functions to work with for Taylor polynomials because when we're looking at the Taylor coefficient, e to the x is that really handy function that has the same derivative every time. So while tables are helpful, you might not need it for e to the x, but certainly make one if you need it. So let's look at T4. T4 is the function's value at 0 divided by 0 factorial for the constant term, plus the first derivative evaluated at 0 over 1 factorial for the linear term, the second derivative evaluated at 0 over 2 factorial for the quadratic term, the third derivative evaluated at 0 over 3 factorial for the cubic term, and the fourth derivative evaluated at 0 for over 4 factorial, for the quartic term. So just note to yourself that if y equals e to the x, then all the derivatives are the same, and that's really convenient. And furthermore, if we evaluate them at 0, they're all equal to 1. So that simplifies the Taylor polynomial to just 1 plus 1x plus 1/2 x squared plus 1 over 6, because 3 factorial is 3 times 2 times 1, x cubed, and then 1 over 24, x to the 4th. 4 times 3 is 12, times 2 is 24. So this is a polynomial that's going to behave like e to the x as long as we stay near 0. So if we wanted to kind of look at that, just to visualize it a little bit, here you can see I put my exponential function in my grapher, and then I went ahead and also entered in the Taylor polynomial. And since I want to stay near 0, I set my window kind of small. I set my window to be on the x-axis from -1 to 1, and then I'm going to go ahead and look at the graph. So there's our exponential function, and then even though we can't see it, you can see on the right that it's actually graphing our Taylor polynomial. And it seems that by choosing the window to be -1 to 1, it's such a good approximation that our calculator can't even tell the difference. But if you wanted to see the difference, you could of course just zoom out, and that would be a much wider window. So there's the exponential function, and then there's our polynomial, which is certainly behaving differently over here because our exponential is not going to grow. And then it starts to be a kind of a poor estimator over here. It appears that for our purposes, when we stay close to 1, that it's actually a pretty good estimator. So that means down here, if I want to use T4 to estimate e to the 0.01 power, that it's going to be approximately equal to the polynomial value when I plug in 0.01 into the Taylor polynomial. So if I do that, I'll get the following. And I am going to go back to my technology to figure out what that is. And I get 1.010050167. That is the value of the Taylor polynomial, and it's an approximate value for e to the 0.01 power. So we're going to use Taylor's inequality again to see just how accurate this estimate is. And so here's Taylor's inequality, that the maximum size of our remainder, or the maximum size of our error, is bounded by some constant m over n plus 1 factorial, and the distance between a and our x value in absolute value raised to the n plus 1 power. And of course this m is determined by looking at the next derivative. So in our case, we're looking for the error in taking the fourth Taylor polynomial. So that means we're going to have this constant m over 5 factorial. Our x value was not shifted. Remember, a was 0. So we're just going to have to look at the maximum value of x raised to the 5th power. So let's go over here and see if we can find this value for m, because we're going to be looking for the 5th derivative of x. But again, remember, this is a really lucky function because all of the derivatives of e to the x are e to the x. And so all we have to think about is whether e to the x is increasing or decreasing, and it's an increasing function. What that means is that it takes its maximum at the right side of our interval. So looking at this interval, if we have an increasing function, then it takes its max at x equals 0.1 for this boundary that we've chosen for our x values. So if we want to figure out the value, oops, sorry, I'm going to plug in 0.1 here. I need to get e to the 0.1, and I can let that be my m value, right? The maximum or this boundary value. And I don't need the absolute value because this is a positive number. All right, also let's think about how x is bounded, but we said that negative 0.1 and 0.1 was where x was living. So in absolute value, that means the largest distance from x is 0.1. So we've got both pieces of our puzzle here to figure out our maximum error. We said m was e to the 0.1 over 5 factorial, and we said the absolute value of x was going to be 0.1 raised to the 5th power. So if I put all that into my calculator, I get a pretty small amount of error. It actually comes out to be 9.2 times 10 to the negative 8. And I think if you remember what we looked at the graph, that this is pretty reasonable, because when we looked at it, we couldn't even visually see a difference. But of course, I'm talking about a TI-83 plus, so it's kind of outdated technology. But at least in this small window, T4 is a pretty good estimator for e to the 0.01. So just for fun, if we just go to our calculator, which ironically is programmed using Taylor polynomials, and I just ask it to compute e to the 0.01, it gives us the exact same thing that our Taylor polynomial did. Guys, because your calculators are programmed as Taylor polynomial estimators. So at glance, we would say there's no error, but of course that's not true, because your calculator, has some bounds to its ability and accuracy in decimal places and things like that. So that's how we can use Taylor polynomials to estimate things that are not polynomial in nature in their natural state. So I hope you enjoyed.